All right, can I get everyone's attention? We'll get started. First of all, good afternoon. My name is Riley Edwards, and on behalf of all of us here in Railtech, we want to welcome you to the William W. Hay Railroad Engineering Seminar today. We got a really exciting seminar. A few announcements before I further introduce today's speaker. First of all, if you have a phone, please silence it so we don't disrupt the presentation. Secondly, in the event that we have severe weather and we need to evacuate, you can exit through either the doors on either side of the room, go downstairs, and we'll convene by the Civil and Environmental Engineering building to our north across the street. Please use the buddy system. Note who is to your right and left, and we'll make sure that we get everyone out safely. So the William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois. On behalf of Railtech, I want to thank the AAR, BNSF, CN, Hanson Professional Services, and the FRA-funded National University Rail Center of Excellence for their support of Railtech and the University of Illinois. It's greatly appreciated by all of us here on campus that work on a daily basis, and I know it's appreciated by you all online connecting to the seminars. Today we have more than 260 people that are registered for the seminar, hailing from 8 different countries and continents. The list of attendees today, we have passenger and freight railroads, transit organization, research organizations, suppliers, and other academics, so we're very pleased that you can join us. If you wish to receive PDHs, could get a PDF, PDHs for your participation today, please see the instructions in the email announcement that was used to let you know about today's event. So I want to make a special announcement before I introduce today's speaker, and it's appropriate that I make this announcement today because our speaker, Dr. Kevin Oldknow, is connected to this particular event. In a couple of months, in April, the dates are up there, the 22nd through the 24th, there's a key conference that's taking place down in Dallas. This is the Wheel Rail Interaction Conference. There's 2 elements to it. There's a principles course on Wednesday the 22nd, and then there's a heavy haul conference the following 2 days, the 23rd and the 24th. This conference was founded by Gordon Baczynski. Many of you may know him. Gordon deserves a lot of credit for the impact that he's had through this conference, and his enthusiasm about rail engineering and education is very contagious, especially to those of us that are academics. So I want to make note of this conference and especially thank Gordon for his intentionality in reaching out to us at the New Rail Center to allow us and invite us to be the presenting sponsor for this event. I'm excited to go down there and see our speaker today present again. I'm going to be a part of the event, and we're really grateful to partner with Gordon and the Wheel Rail Seminar Group. So with that, I'd like to announce today's presenter and the abstract for his presentation, Dr. Kevin Oldknow. For the abstract, railway vehicles and tracks are complex. I'll advance here. Railway vehicles and tracks are complex, sophisticated, and highly nonlinear systems. There's one singular location where these systems meet and interact, and it's called the wheel-rail interface. The contact pressures and subsurface stresses that are generated in wheel-rail contact far exceed those seen in many other engineering applications, as does the range of environmental conditions that you see at this truly open interface, the wheel-rail interface. This leads to some fascinating phenomena and research questions that we need to understand and solve. Today's seminar is going to include a review of wheel-rail contact fundamentals, connecting them with more recent developments in the understanding of critical dynamics and damage modes that have a profound consequence on railway systems and their cost efficiency and safety. Finally, our speaker is going to discuss some open questions, areas of research related to modeling and simulation, machine learning and other sensing technologies, and how these are used to further understand, measure, and manage the wheel-rail interface. So I'm excited to introduce our speaker today, Dr. Kevin Oldknow. He's an associate professor at Fraser University in Canada and is the principal investigator of the Vehicle Track Research Group there at Fraser. Dr. Oldknow was the inaugural director of the School of Sustainable Energy Engineering and currently serves as the school's graduate program chair. He has researched and published in the areas of dynamics and controls, wheel, rail, and vehicle track interaction, tribology, and other friction control and engineering education. Dr. Oldknow has more than 20 years of industrial experience, primarily in railway systems, which has included a variety of projects in both passenger and freight railway systems, mostly related to vehicle track studies. Over the course of his career, he has held technical, strategic, and senior management roles at Procter & Gamble, Chameleon Controls, and other Portec Technology, L.B. Foster, and some other companies. I want to say on a personal level, it's been an amazing couple of days to spend time with you, Kevin. We've had great exchanges, and I look forward to collaborations going forward. So I'd like to welcome up Dr. Kevin Oldknow, who's going to present today's HAY seminar titled Contact Matters, Wheel-Rail Interface Fundamentals and Frontiers.
So thank you very much, Riley, for the very kind introduction. It is a privilege and an honor and a thrill to be here and to give this talk today. I'm grateful to Riley and to Marcus and the entire RailTech team. I'm about to go through a whole bunch of names and realizing that I'm not going to have time to do that. I have to say Arthur, who picked me up at the airport and delivered me safely to the hotel. So thank you very much, as well as many, many other things in this visit. But thank you very much, the entire RailTech team. I really enjoyed interacting with everyone I've been able to interact with while I'm here. Likewise, I'm very enthusiastic about the future and to continuing the discussions that we've started. I'm also very grateful to everyone who's chosen to spend their time in the room today, and to those of you who are attending online as well. So, as you've heard already, my name is Kevin Oldknow, and I'm an associate professor at Simon Fraser University. What I'm going to do in terms of flow is first start with a very brief introduction to SFU, just in case you're not immediately familiar. So Simon Fraser University is located in the Greater Vancouver area on the west coast of Canada. So starting at our largest scale of resolution, we're here in this southwest corner of British Columbia. If we zoom in a little closer, we've got 3 campuses in that area. We've got our main and original campus at the top of Burnaby Mountain. And then we've got 2 other campuses, one in the downtown Vancouver area and one in the city of Surrey. My own work mainly takes place in the city of Surrey. To give you just a little bit more introduction into the university, first of all, this view is of our Burnaby campus sitting on top of Burnaby Mountain, so it's a particularly breathtaking place to be at certain times of the year. I suppose there are other times of the year when the clouds have socked in and you can see nothing and you might as well be anywhere, but on days like this, it's a good place to be. At SFU, we have now 9 different faculties in the university. Faculty of Applied Sciences, which I'll expand upon in a minute. The rest that you see on the list are long-standing faculties in the university, with the newest, though the exception to that, being our School of Medicine. So our newest addition to the university is a School of Medicine, which is a very, very recent development for us. The Faculty of Applied Sciences at Simon Fraser University further breaks down into 4 schools or academic units. They are basically the same as an academic department. So our 4 schools are our School of Computing Science, which is the longest standing and the largest, our School of Engineering Science, which is the second longest standing and second largest, our School of Mechatronic Systems Engineering, and then most recently our School of Sustainable Energy Engineering, which was launched in 2019. And I was very lucky to be very close to that project as it unfolded, and that's now my academic home, is in the School of Sustainable Energy Engineering. What you're looking at here is the expansion to our Surrey campus that was constructed in conjunction with the launch of the new program and its associated research. Okay, with that out of the way, to give you a bit of an overview of the presentation, which parallels what you heard in the abstract, I'm going to spend the first portion of the time, probably about half the time, going through some wheel-rail contact fundamentals to lay the foundations and the framework for understanding the types of problems that we're looking at here. And then in the second part, what I want to talk about is some important insights that those fundamentals allow us to gain, some important phenomena that they allow us to understand. Some of those are what I call low frequency in the vehicle track world, low frequency phenomena, and some of them are high frequency. And then the last part of the talk will really be about open questions, and by that I mean open questions amongst the broader community, not only our research group at SFU, just more broadly in wheel-rail interaction, and then some of the projects that we are immediately and intimately involved in the group. Okay, so to get going, if we're going to start thinking about wheel-rail interface and wheel-rail contact fundamentals, the first thing we have to do is try and place ourselves right inside the wheel-rail contact area. And we might think that getting as close as this is good enough. I would argue it's not. I think we need to get closer. And so we probably need to start looking a little more closely like this. I would argue that's still not close enough. And in fact, what we really need to do is try and put ourselves right inside that very, very small space. And one of the things that I've advocated many times when presenting is that when we're thinking about some of this stuff, it's sometimes a fun toy analogy to imagine ourselves in this space and imagine that the floor under our feet is the surface of the rail and that the ceiling above us is the surface of the wheel. And we are in this very dangerous seeming space with a lot that's going on. But one of the things that's important is there is some physical separation between those two things, and we're going to find out that that is the reality as well, and that's an important part of the equation. So as we go through this, maybe from time to time, just imagine yourselves right inside that wheel-rail interface, right in the contact between the two surfaces, and imagine what's being experienced there. Once we're inside there, what we need to think about, again, is this separation. There really is a separation between the two, and sitting inside that separation is something that we call the third body layer. I'll say some more about that a little later on. But this third body layer is built up of a number of constituents, some of them generated through wheel-rail interactions, some of them external contaminants. But it does the job of accommodating displacement between the two surfaces. So as we'll talk about, what is always going on during wheel-rail contact is those two surfaces are moving in some way relative to each other. There is almost always some relative motion between the surfaces of the wheel and the rail, and it's the job of the third body layer to accommodate that, to find some way to accommodate the relative motion. So what I'd like to talk about now is what I think we can call the language of wheel-rail contact. And what I mean by that is, as Riley mentioned in the introduction, you've got these two very complicated systems, dynamic, nonlinear, sophisticated systems in the rolling stock and in the track. And they come together through their wheel interface. And it's fun to think about in what ways can they talk to each other. So what are the means that they have to communicate through this interface? And I'd argue that there's two. The first is contact pressure and geometry, and that's what we call the normal problem. So the first way that these two things interact and exchange physical information, if you like, is through contact pressure and geometry, and we call that the normal problem. The second element that they have in the language is traction and creepage, and what I mean by that is this notion of relative motion. So relative tangential motion between the two surfaces gives us traction and creepage, and this is what we tend to refer to as the tangent problem. So these two problems, or these two modes, give the opportunity for exchange between the wheel and the rail. So we'll go through each of those one at a time. The first one, the first fundamental, is contact pressure and geometry. And so I want to ask just a couple of toy questions. The first one is, if we take a perfect circle, so perfect geometric circle, and we bring to that circle a perfect straight tangent line, what is the length of contact of a tangent line that is just immediately adjacent to a perfect circle? The answer is 0, right? The length of contact between a tangent line and a perfect circle is 0. Okay, that didn't look much like a wheel and rail. This looks a little more like a wheel and a rail. So now let's extend that and think about a perfect cylinder and a perfect plane. So if I bring a perfect cylinder, which is starting to look a little like a wheel, in contact with a perfect plane, now there's a line of contact. What's the area of contact between those two? It's also 0, right? The area of contact between a perfect cylinder and a perfect plane is 0. Next question. If I tell you about force and I tell you about area, how do we calculate pressure? Force divided by area, right? If I want to know about pressure, I take force and I divide it by area. So if I take a cylindrical body, which is a rough approximation to a wheel, and I bring it into contact with a planar body that's a rough approximation to a rail, and I apply a vertical force F, and I have 0 contact area, what's the contact pressure between the two things? It's infinite, right? You're dividing something by 0. And so that tells you that a whole lot of things are going to fail and fall apart quickly if that's what's going on. So clearly that is not what's going on, right? There's something else happening. And that's what brings us into this notion of the contact patch and the normal problem. So what happens in reality when you bring two bodies together under load, two curved surfaces, is that the centers of those two bodies approach each other by some small amount, and we end up with a deformed area that gives us something called the contact patch. And the typical images that we see here correspond to what we call Hertzian contact. Hertzian contact is what we get when we bring two surfaces together with constant radii of curvatures. So it could be a cylinder and a plane. It could be two cylinders, two spheres, just things that have constant radii of curvature. And under a specific set of conditions and assumptions, they give us this elliptical contact area. So in this image, what we're looking at is interference fringes. So in these experiments, what happened was a couple of bodies were brought into contact, and we get these interference fringes, which are constructive and destructive interference patterns of light as we move away from the contact area and the bodies slowly separate. And what we can see is that as we move from an unloaded case to a loaded case, we get an expansion of this contact area, and the contact ellipse grows. So that can give us something like line loading. In this case, what we're looking at is contact along a straight line. And now instead of looking at those interference fringes, we're looking at elastic fringes showing subsurface stresses. And the first thing, or one of the first things that you can notice, is that the point of maximum shear stress sitting under that contact is not right at the surface. It's a little bit below the surface. Typically, in a rail setting, that's a couple millimeters. That ends up becoming important for some phenomena. We can also look at point loading, and this is what happens when we bring a sphere into contact instead of a cylinder. Each of these starts to reflect different types of wheel-rail contact. We see a similar response. It looks a little bit different, but we still see the case where we've got a point of maximum shear stress occurring at a depth below the surface. Okay, so in realistic conditions, there are times when we approach Hertzian contact. What we're looking at now is a simulation run using the contact library invoked through MATLAB, in which we're bringing together a measured rail profile and a measured wheel profile. We are applying a load, and we are looking at the contact pattern that emerges as well as the pressures at the surface. What you'll notice is that in this case, we're talking about contact between the tread of the wheel and the top of the rail surface. In that case, the conditions are something like the Hertzian assumptions. So we end up with contact that looks something like a Hertzian contact ellipse. It's not too far off. And in these kinds of conditions, it's not unreasonable to approximate the system as Hertzian. But then we also get other kinds of conditions that don't look like that. So this is a case where we're bringing a wheel into relatively conformal flange contact. We can see contact between the throat of the wheel and the gauge corner and up towards the top of the rail surface here. So contact is distributed over a couple of areas. It's bracketing a fairly tight radius of curvature, and it's got a couple of clear kind of modes in the contact. So this is a very common example of the type of contact that we run into once we do get into something like flange contact, and it is very clearly no longer Hertzian. So we have to look at these things as being more complex and requiring a different kind of understanding and depth of analysis. So that was fundamental one, right? The normal problem where we're exchanging information through pressure and force. Fundamental two is this notion of traction and creepage. And so creepage occurs inside that contact area in three ways, in what we can call longitudinal, or what are called longitudinal, lateral, and spin. And so there's a sander in this video you can ignore. Just focus, if you don't mind, on what's going on between the wheel and the rail. So one way to understand longitudinal creepage is to realize that as that wheel is rolling along, it's contacting the rail in different points as it kind of wanders around. And as a consequence, it's contacting along different wheel radii because of the taper of the wheel. And so it won't always be the case that that wheel is simply rolling along smoothly. There will be times when it is rolling a little faster or a little slower, and we'll end up with small amounts of longitudinal slip relative to the rail. We also get that in conditions of traction, if we've got locomotive adhesion. That will also give us some small microslip that gives us longitudinal creepage. Lateral creepage we can think of as the sideways motion of that wheel on the rail. And that's going to happen in curving, as we'll see in a minute, but it also happens fairly generally. That is not a static scenario. The wheel is moving laterally as it negotiates the track, and so that's giving us some degree of lateral creepage at the same time. And then spin, that we'll talk about a little more, is something literally like spinning a coin on the tabletop. It's a spin creep between the wheel and the rail. Okay, so having looked at those kind of illustratively, we can look a little more rigorously and say, all right, well, what does longitudinal creepage mean? And what it means is, or the way it's defined, going back to Carter and Fromm, is this ratio. So R is the wheel radius, omega is the wheel's angular velocity, and V is the forward velocity. We subtract the forward velocity from the product of the radius and the angular velocity, and then divide, we normalize by the forward velocity, and it gives us this number that we call longitudinal creepage. So if our wheel is spinning faster than it would if it were just rolling along freely, we get positive longitudinal creepage. If the wheel is spinning slower than it would to just roll along freely, we'll get negative longitudinal creepage. And so that's essentially how both traction and braking are delivered through the interface, is through positive longitudinal creepage or negative longitudinal creepage. So what does this look like inside the contact? I'm going to run this animation twice. This is showing the contact solution under different states of longitudinal creepage. This is our contact area. We've got 0 lateral creepage and 0 spin creep, but we're going to advance the longitudinal creep, and we're going to see an increasing amount of creep, and we're also going to see an area of stick and slip that advances towards the front of the patch. So I will run this again, but the way to imagine this is the forward direction of travel is to the right. We've got some relative motion between the wheel and the rail in the contact area. The more slip there is, the larger this area of slip is, and the smaller this area of stick is. So I'll run that once more, and the things to watch are these little arrows, which are telling us about the vectors of the traction force happening inside the contact area, and this boundary, that's the boundary between the leading part of the contact that is in a stick state and the trailing edge that is starting to slip as that boundary moves forward. So what happens is, as that area of slip increases, as we develop more and more longitudinal creepage, what we develop is more creep force or more friction force. And it ends up looking like this. As we advance and gain more and more longitudinal creepage, so as that slip area moves towards the front of the contact patch, as we're slipping more relative to the rail, we get more and more friction force until eventually we saturate. And generally we can think of that saturation happening once the entire area is in slip. So once we've run out of stick area, the entire contact area is in slip, we're now saturated, and that roughly sits at the product of the normal force and the coefficient of friction. Same thing is true in the reverse direction, which is how we get braking. So if we have negative longitudinal creepage, then we will develop a negative or a braking friction force until eventually we saturate that. Okay, so lateral creepage. We can think about lateral creepage as occurring very commonly in curving. When I run this animation, what I'll ask you to look at is our 2 images up top, which are our leading axle at the high rail and low rail, and our trailing axle at the high rail and low rail. And what we'll see is that as the vehicle enters the curve, our leading axle shifts out towards the high rail. We get gauge corner contact here. We can see that the low rail wheel has shifted substantially, whereas the trailing axle has stayed more centered. What that's illustrating for us is an angle of attack that vehicle has taken up throughout the curve. So as that railway vehicle has negotiated the curve, it has taken up an angle of attack, and as a result of that angle of attack, the leading wheel set is seeing a lot of lateral creepage as it works its way through the curve. Okay, since it's pointing with an angle of attack, in order to keep moving in the intended direction, there must be some lateral creepage that's happening at the same time. Spin creep, this one can be a little bit elusive, but it's not bad once you get your head around it. I mentioned it's kind of like spinning a coin on a tabletop. The way to picture spin creep is, let's imagine we are looking down on the wheel rail contact, and we are looking at this wheel that has a taper to it. So it has a conicity to it. And what we know is that as this moves forward, the wheel is going to rotate. And if each of these points start together on the forward-facing edge of the wheel, they're going to arrive at the bottom edge at the same moment. Right? So if they are in line with each other facing forward, they will still be in line with each other as they reach the bottom. But what we know from the physics of the situation is that since this radius is smaller than this radius, this point has a farther distance to travel than this point. So they're going to start together on the leading face of the wheel. They're going to rotate underneath. They're going to arrive together underneath. But this point has traveled a farther distance than this point. So that means there's a differential in the creep across the contact area. And if our central point here is just in neutral free rolling, then that means our point on the smaller radius is actually in a state of braking, and that our point on the larger radius is in a state of driving. So if you look at that as a cross-section across the contact area, what you see is something that ends up looking like a spin. And so this is where we get spin creep from inside the wheel rail interface. The net creepage is some combination of all three, which gives us a fun question to think about. Imagine for a minute that we have saturated our longitudinal creep. Okay, so imagine we've got enough longitudinal creep, we've saturated creep in the wheel rail contact, and now our longitudinal creep force is approximately mu n, right? Saturated friction. Imagine we have simultaneously saturated our lateral creep. And so our lateral creep force is also mu n. That would suggest that the resultant creep force is the vector sum of those two. But the maximum friction force in any direction is mu n. There is no way to have more friction force than mu n in any direction. So that means you cannot simultaneously saturate longitudinal and lateral friction. And in fact, they must interact. And so that's what we do see, is that if curve 1 here is what you get in terms of longitudinal force versus longitudinal creepage, as you introduce different types of creepage, lateral and spin, they interact with each other. And the total amount of longitudinal force that's available ends up being affected by the presence of the other types of creepage. So a couple more animations to look at really quickly. In this case, what we're doing is starting in a state of 0.3% longitudinal creep, and we're adding lateral creep to watch how the contact evolves. And so we can see those two modes of creep kind of sharing the interaction, and we can see how the overall contact condition changes. And then spin, this one I find really fun to look at. What we're doing here is starting with longitudinal creep, and we're introducing spin creep into the mix with no lateral. And we can watch how that interaction unfolds inside the contact area. So maybe it's just me. I find that fun and elegant to look at. So we can imagine all these things happening at the same time. There's some combination of longitudinal, lateral, and spin creep happening generally all the time, and that is determining what's happening with our friction forces coming out of that interface. What I mentioned at the beginning of the session is that we also need to remember that although it's tempting to think about wheel rail contact as intimate steel-on-steel contact, it almost never is. There is almost always a third body layer separating those two faces, mainly made up of iron oxide wear debris, but often made up of other contaminants as well, either environmentally introduced or intentionally introduced. And that third body layer, which is shown here in a micrograph just to prove to you I'm not making all this up, does the job of accommodating displacement. And the way that it reacts gives us the real behavior of this traction creepage curve. I've showed you the theoretical curve that says as you increase creep, you get increasing friction force until it saturates and then stays neutral. In real systems, we can have neutral friction, or we can have falling or negative friction, where we actually see friction force roll off after the point of saturation. Or we can have rising or positive friction, where that friction force continues to increase past the point of saturation. And of the three, falling friction is the most commonly occurring in natural systems. So when you're out on track looking at a steel wheel on a steel rail, more commonly than not, the condition is one of falling friction between those two surfaces. Okay, so those were the fundamentals. That was kind of the building block session that was meant to lay the groundwork so that we can think a little bit about some key phenomena and then look at the more recent research questions as well. Talk a little bit about low frequency examples, and what I mean by that in this case are curving forces and things like wear and rolling contact fatigue. These are not the only examples of things you can understand with wheel-rail fundamentals. They're just a couple of illustrative ones. And then high frequency will be corrugations and curving noise. Okay, so let's talk about steering forces, and then we can talk about curving forces, and we can talk about stability. Let's imagine now that instead of just a wheel and a rail, what we have is a wheel set. And that wheel set is arranged so that it is perfectly centered. We have the conicity of the wheels, and because it is perfectly centered, each wheel is running on the same rolling radius. Now what we do is give that a nudge. We move it to the right. As soon as we've done that, what we've done is displaced the wheel set so that the right wheel is now running on a bigger rolling radius, and the left wheel is now running on a smaller rolling radius. Based on what we've already seen, we can then say, if both of these things are running on the same rolling radius and just freely rolling along, then this is where we sit on the traction creepage curve. There is no longitudinal creepage, and so there is no friction force. We're just freely rolling along. As soon as I have nudged this wheel set to the right, and I'm now running on a larger radius on the right wheel and a smaller radius on the left wheel, my larger radius is going to push me into a state of positive longitudinal creepage. And I'm going to see a positive creep force. My left wheel is going to push me into a state of negative longitudinal creepage and give me a negative friction force. The way they end up acting on the vehicle looks like this. My positive creep force points forward. My negative creep force is a braking force pointing backwards, and that's going to steer that wheel set back towards the center of the track. So that kind of puts together this notion of creepage, of traction forces, of rolling radius difference, and how that generates steering forces. Now, the rate at which those forces develop with lateral displacement depends on this notion of the rolling radius difference. And you see that expressed in these kinds of plots, where this is a plot of the difference between the radius of the right wheel and the radius of the left wheel at the points of contact as it is displaced. So as I displace the wheel set to the right, my right wheel is getting bigger, my left wheel is getting smaller, and so the difference between those two is positive and growing. If I displace it to the left, my left wheel is getting bigger, my right wheel is getting smaller, the difference is negative and falling. And the slope of that is telling me how quickly that change in radius is occurring, or how aggressively the wheel set is going to steer. The steeper this slope is, the faster the effective difference in radii is changing, and the higher the steering forces are going to be. Anyone want to say what's going on with these approximate vertical spikes? What's happening there? Wheel flange, exactly right. Yeah, so what happens is as you engage the wheel flange, suddenly that wheel is getting much bigger very quickly. And so that point where the rolling radius difference plot takes off is the point where your wheel flange is now engaging. One of those wheels is starting to get very, very big, very, very fast. Okay, so let's now take all this and put it into the case of curving forces. We're going to put ourselves in a sharp curve, which means we have run out of rolling radius difference and we have engaged the flange. Let's think about what's happening with creepage. At the trailing axle on the low rail, we've got the case where the wheel set is more or less centered and radially aligned. And in that case, we have a state where the creepage is primarily longitudinal creepage. That radius is bigger than it would like to be, and so it's in a state of driving positive longitudinal creep. Trailing axle at the high rail, similarly, that wheel is smaller in radius than it would like to be. As a result, it is in a state of negative creepage and generating a braking force. Leading axle at the low rail is primarily in a lateral creep because of that angle of attack. And because of that lateral creep, we get a lateral creep force. And then at the high rail tread, we get a similar effect. Because of that angle of attack, the high rail tread is experiencing mainly lateral creep, which leads to a lateral creep force. The high rail flange is a different matter in the story. So at the high rail flange, as we've just said, as we had correctly answered we have a sudden rapid increase in radius, and so a very large rolling radius difference and a very large positive longitudinal creep, which leads to a creep force. Now, if I look at each of these are the forces acting on the vehicle. And think about, what is each of these forces doing? Is it trying to help the vehicle stay in the curve or trying to steer the vehicle out of the curve? And the answer is every one of these forces, except for the force at this flange, is trying to actively steer the vehicle out of the curve. Okay, so what's keeping us in the curve is a reaction at the flange. And our track ends up feeling this. So our track ends up feeling these track spreading forces, which are the net sum at each rail, and also these longitudinal creep forces at the trailing axle. So having looked at all of that and thought about it, when we're talking about negotiating sharp curves, higher equivalent conicity, meaning a steeper slope on the rolling radius difference graph, is generally good. It generally makes us happy. It means we're going to steer better around shallower curves. We're going to get through sharper curves before we engage the flange. Okay, now what about tangent running and stability? If we look at this wheel set again in tangent track, and what we do is give it a nudge, what we're going to find is with that initial nudge, we will get longitudinal steering forces in the way that we've talked about them. And as a result of those, that wheel set will approach the center line of the track at an angle and with a given velocity. If the overall velocity of the system is relatively low, then it will end up resulting in a set of oscillations that eventually die out. But there's a speed above which those oscillations will not die out, and we'll end up with a bifurcation that leads us to the hunting phenomenon. And we see this in the real world. Gary Wolf very kindly provided this video to include. So it's a fairly violent interaction between the wheel set and the track. And that is due to the onset of this hunting instability that's coming from our creep forces. So when it comes to stability in tangent running, higher equivalent conicity is generally bad. It's generally going to bring us the onset of instability at a lower speed. And so it's a classic engineering problem. Right? What is the right level of equivalent conicity to have? It really depends on your system. It's a classic trade-off. Okay, what about friction? What about wheel rail friction? What we know is that there are cases in which the gauge face of the rail is intentionally lubricated and the top of the rail is intentionally managed at a given friction level. What does that do for our steering forces? Lubrication, if we picture it, has the effect of reducing the available friction on that gauge face. And we know that this interaction was the one and only place where we were generating a positive steering force. So gauge face lubrication, a little bit counterintuitively, is actually going to rob us of steering and make our lateral forces go up. Right? It's counterintuitive. Gauge face lubrication brings wear down. It brings energy down, but it makes lateral forces go up because it's robbing us of that steering force. The introduction of top-of-rail friction control then affects each of the other forces in the system, and every one of those was a counter-steering force or an anti-steering force. So the introduction of a change of top-of-rail friction has the effect typically of reducing all of those other forces and therefore bringing the curving forces down. As an example of that, we can see some work that was done on a passenger rail system that was looking at these effects. So in this case, this is a histogram showing L over V ratio, meaning lateral over vertical force. Higher L over V means a higher lateral or lower vertical force. And what we're looking at here are conditions that include the application of top-of-rail friction management, the application of gauge face lubrication, and a case that has no lubrication at all. And what's interesting is if we compare the case with no lubrication at all and look at the histogram of L over V values and compare that to the case with gauge face lubrication, we can see really clearly that those lateral curving forces are going up. So that might make us worry a little bit about derailment coefficient, but making the coefficient of friction on the gauge face lower also makes it harder to climb. So even though we're increasing lateral curving forces, which might seem like it's increasing the risk of rail climb, we're also making it harder to climb that rail. And so overall, the risk of derailment tends to reduce. Okay, another low-frequency phenomenon, long time period phenomena is rail and wheel wear. And we're used to seeing images like these that show us the worn states of each. These are plots showing us how we tend to, or diagrams, I'm sorry, showing us how we tend to measure these things. What ends up being convenient is that the mechanisms that dominate wheel and rail wear tend to be well suited to modeling through what's called an Archard wear law. And that gives us some important insights that let us understand the impacts of various factors. One of the things that you'll see in this law, which is telling us that the volume of worn material is proportional to the normal load between the two bodies and the sliding distance between the two bodies, and inversely proportional to the hardness, is also proportional to this constant C. That is in turn proportional to the coefficient of friction, and what we can show is we can arrange all of this to show that the wear volume is proportional to sliding energy, and that ends up becoming important later. Shakedown and rolling contact fatigue. So this is a chronic issue in many rail systems, where we have the formation of rolling contact fatigue cracks, like we can see here. They can be gauge corner cracking, head checks, top of rail fatigue, and so on. In some cases, this can develop into something that is not pretty to look at, but not inherently dangerous when we get these kinds of shelling out events. And in others, though, we can end up with really severe risk associated with transverse defects in rail brakes. What the fundamentals of wheel-rail contact have allowed for is an understanding of the rolling contact fatigue mechanisms in terms of this shakedown map. The way to think about this and understand it is we've got on the x-axis the traction coefficient T over N. So how strong is the traction force acting at the surface? On the y-axis, we've got the peak pressure P0 divided by the material shear yield strength. So how strong is the peak pressure pushing down, and how strong is the material? On the underside of this curve is the area in which shakedown occurs, which means that the system can arrive at a plastically deformed state where through work hardening, ultimately it is in a state of happiness and kind of equilibrium. Whereas above this curve, we enter a phase of ratcheting. And ratcheting means that very small accumulations of plastic flow are eventually going to exhaust the ductility of the steels and lead to the creation of these RCF cracks. What's interesting here, I think, is it connects to this insight of seeing that point of maximum shear stress sitting below the surface of the rail. In that when we apply pressure between a wheel and a rail, we initially get a point of maximum shear stress sitting directly underneath. As we increase the traction coefficient, that point of maximum shear stress starts to move closer to the surface and grow in intensity, which is why out here, where we have large traction coefficients, it takes smaller peak pressures to enter a state of ratcheting. So again, it's this combined effect of both the normal pressures and the tractive forces that are producing ratcheting and ultimately leading to RCF. Going into high frequency phenomena, corrugations is one in which we have these periodic damage patterns, often connected to wear as the fundamental mechanism. And the fundamental insight is that we can understand these through thinking about a wavelength fixing mechanism and then some damage mechanism, most often wear. Those produce these interactions between normal load and slip that lead to a various range of formation mechanisms for corrugation. Corrugation work has continued well beyond the initial work that's cited here and gotten more and more complex in looking at multiple modes of vibration, both the vehicle and the track, and then comparing the effects of friction states, both high and low friction, understanding how they affect in turn both the T over N forces and the amounts of creep. And what we're looking at here is a case where having higher state of friction gives us higher T over N forces and higher amounts of creep. Lower state of friction gives us lower of each, and that in turn tends to suppress the onset of corrugations. Now to the one and only audio clip in the entire presentation. Another thing that wheel rail fundamentals have let us understand is curving noise. Curving noise can come about in a number of different ways. One of the interesting ones is curve squeal, and I'm going to play a clip now. We'll see what the volume is like. So curve squeal is that recognizable single tone noise mechanism. It's not the grinding or hissing noise that we get with flanging. It's a single tone, and that tone is coming from excitation of the wheel web in a way that it ends up acting like a loudspeaker. So we have a frictional condition at the wheel rail interface where sometimes through this falling friction mechanism we have an instability mechanism, and that instability mechanism can allow for excitation of the wheel web in a specific mode that results in this squeal noise. So again, that work is continued, and what we see is that manipulating the friction between those two bodies is an effective way to end up suppressing the noise mechanisms, either through reducing friction or through changing the post-saturation slope. Okay, I'm going to talk very briefly about a couple of open questions in the community, and these are in the broader research community, not specific to our group. First is arriving at a unified model of wear in RCF. Second is understanding the white etching layer. And the third is finding a common understanding and language for squats and studs. So what do I mean by a unified model? What we're looking at here is two images of dye-penetrant measurements taken off rails that faced very, very similar operating conditions. And in one case, what we see is a relatively clean surface, meaning this rail has seen a lot of wear, but has not seen a lot of rolling contact fatigue development. This surface has seen a lot of rolling contact fatigue development. And the question is, why does one dominate the other in a given setting? The most practical approach that we've come to understanding and gets used quite often is what's called the T-gamma approach, or the whole life wear model. Whole life rail model. And what it says is if we look at the energy spent in contact, we can expect that we will move from an area in which RCF dominates as the damage mechanism to one in which wear dominates as the damage mechanism. This has ended up being useful as a practical tool in a number of different places. It doesn't end up explaining everything. And so there's still work to do here. I think this has been a fundamentally important insight, but it's not the end of the story. And we do see cases where both RCF and wear move together. So a reduction in one is accompanied by a reduction in the other. That doesn't perfectly align, and it tells us there's a clue in there that there's more to understand. The white etching layer is something that's become a particular point of focus amongst the broader community quite recently, over the last number of years. This has to do with what we see when we etch rail and wheel steels to get an insight into the grain structure. And what we see is that there are often areas that simply do not etch, and then they show up in the micrograph as a white area or a white etching layer. And typically they are not etching because they've either undergone a high thermal intensity process, so there's been a wheel flat or a skid or something that's introduced a high temperature, high thermal input, or they've gone through a very high shear process. And there's a lot of open questions and open research in terms of what the interaction or interactions is or are between these white etching layers that appear and crack initiation sites. And that particularly ties to our understanding of something called studs, which is what I'll talk about now. So another open question, and there's a vibrant dialogue internationally about this, is looking at finding a common language for squats and studs. So on the left, this is a squat. And we can recognize it by the widening of the running band, the sort of V shape here, the two dark lobes. It's a defect that is particularly dangerous, is well known, and derived its name from someone looking at it and saying, you know, I think if a particularly heavy garden gnome squatted on the rail, we would see something like that. Well understood. This is not a squat. And this has led to a lot of confusion in the industry. Okay, so this is a squat. This is not a squat. It is very, very difficult to tell the difference looking at the surface. To understand the difference, we need to look beneath the surface. And what we see is that a squat is formed as a rolling contact fatigue ratcheting-based mechanism that can lead very quickly, or not very quickly, eventually, to a transverse defect and a dangerous rail break situation. Whereas a stud tends to involve cracks that kind of meander along, near the surface, but don't really present real imminent danger. These form very slowly under particular conditions. These form very quickly. So we're talking 100 MGT, let's say, versus 15 MGT. And where we can see the difference really is looking at the grain structure. What we can see is a squat has experienced substantial ratcheting and plastic flow, whereas a stud, for reasons that are still being understood, just seems to wander around and follow the grain boundary. We have good insights, but it's not an answered question, at least not a completely answered question. Okay, in my closing few minutes, I just want to tell you about a few projects that are going on in the vehicle track interaction research group at Simon Fraser University. The pictures on the left are some of the wonderful people, wonderful students that I've had a chance to work with over the last several years. And our overall motivation is around helping the rail industry to both understand and manage the wheel-rail interface. We see that as leading to increased utilization and asset life extension, and in turn that leading to improvements in energy efficiency and emissions, as well as embodied carbon footprint. The 4 projects I'll touch on very quickly are conformal contact simulation with measured profiles, implementing third-body layer friction models, estimating wheel-rail friction based on dynamic vehicle response data, and near-surface RCF depth characterization. So we've looked at these contact simulations, and what becomes tricky is that when we run contact simulations with perfect as-designed profiles, they give us meaningful results, and that's great. When we run these contact simulations using measured profiles, those profiles contain some combination of what is real surface roughness and some artificial measurement noise, and they occur at overlapping wavelengths that make them very difficult to untangle. So when we apply some pre-processing and smoothing and run that through our contact library, we can get results ranging from this at very low amounts of pre-processing to this at very high amounts of pre-processing. This seems artificially spiky. The peak pressures are unreasonably high. This seems satisfyingly smooth, and the peak pressures are much lower. But knowing what the truth is nearly impossible. So what we need to do is come up with some practical way to decide how much filtering to apply. So as a fairly simple experiment, what we did was run a surface roughness tester over a limited range of profile, and then also ran one of our typical measurement instruments and looked at the differences in the repeatability of those profiles as well as the roughness content. So here we're looking at the wavelengths over which roughness is occurring and the contributions to the overall shape, as well as this presence of noise that we need to try to eliminate. So to do that, I've been collaborating with Edwin Vollebrecht over at VTech CMCC in the Netherlands. And Edwin's put together a really nicely effective splining approach that lets us filter these profiles at given cutoff wavelengths. And we've been doing work to understand what is the wavelength at which we maximize the suppression of noise without starting to influence the overall shape that we're trying to understand. So this has been an important bit of work in trying to get these contact pressures right. Third body layer friction models in vehicle track simulation. What happens is when we run vehicle track simulations, the friction model tends to look like this. So this is the traction creepage curve we've been looking at today. This is a more realistic traction creepage curve from 2 different friction states off a test stand. And the thing I want to call your attention to is that at these low creep values, the classic model has almost no difference between those traction creepage curves, whereas the realistic conditions show big differences across the 2. What that means is that at low curvatures, in shallow curves where we're at low creepages, our simulations are getting it wrong. And in those low curvature states, we can see a lot of important phenomena emerging. So there's motivation to get this model right. What you're looking at here is a third body elastoplastic layer that goes along with this notion of the third body layer. This was developed by Kalusik and others a number of years ago. And what it does is explain phenomena in terms of a third body layer between the 2 surfaces that is initially elastic, but eventually fails and becomes plastic. And once that occurs, can either continue hardening or begin softening. What that gives us the possibility to do is then use the different parameters of the model like paintbrushes and explore the space of possible traction creepage curves. So here we are affecting the shear stiffness of the layer, the thickness of the layer, the shear yield strength of the layer, how quickly does it break, and what it does after yielding. Does it continue to get stiffer or does it start to soften? So by putting these four kind of paintbrushes together, we can create traction creepage curves that behave like various third body layer model situations. So we've done that and run those through vehicle track simulations, and what we do see is significant differences in our curving behavior. These are curving force plots comparing the standard classic traction creepage curves to some of these third body layer model curves. And what we can see is that particularly in shallow curves, they deviate. They're different to each other. And then eventually, as we get to sharp curves, they do start to converge again, which is what we'd expect. So it's telling us there's something to this. There's something to really trying to accurately model the third body layer. Estimating wheel rail friction based on dynamic vehicle response data. The issue here is that friction is managed all over many networks. What is still maddeningly difficult is trying to verify, particularly, the top of rail friction control systems are working everywhere. So if you've got top of rail friction control systems spaced a couple miles apart, how do you know what the friction coefficient is looking like over that wide expanse? And it's very, very difficult to do that. There's a number of traditional measurement methods, including tribometers, instrumented wheel sets, lateral force measurement sites. They all have a range of limitations. What we're aiming to do is see if we can make use of dynamic vehicle response data coming from vehicles that are already running around in revenue service to infer friction states. From earlier in the talk, what we know is that friction affects vehicle dynamics. Right? We know if we change the friction at the wheel-rail interface, the dynamic vehicle response will change. So can we run that in reverse? Can we look at the dynamic vehicle response and infer the underlying friction state? The strength of the approach is that these vehicles, measuring a number of different dynamic signals, are already running around in revenue service in Australia. And so we're trying to understand if we can use that data in the way we want to. To do that, we combine both a simulation and a field measurement framework. In the simulation framework, we can specify the friction level. We can set it. We can watch what happens with the dynamic vehicle response data. We can analyze what comes out, look for features that make sense, and think about how we interpret those. In the field measurement framework, we cannot specify the friction. Right? We cannot go out into the real world and dictate what the friction is between the wheel and rail. We just can't. What we can do is take a look at the maintenance records for the friction management systems and understand when they were off and when they were on, when they were maintained and when they were put back into service. And from that, we can infer, if you've shut off all your friction management systems, you're probably in a drier state. If you've just serviced them and brought them back in, then you're probably in a well-managed state. And so we can look at it as a classification problem. Compare differences in the dynamic signals from an FM off versus an FM on state. Again, look for features and bring these two together into a machine learning-based friction classification model. We've published some initial results of this recently at IHHA and are looking forward to some more substantial publication a little later this year. The last piece of the puzzle, and I know I'm a minute or two over, this is the very end, is near-surface rolling contact fatigue depth characterization. The challenge here is that we want to manage the development of rolling contact fatigue by removing it. We remove it by grinding, sometimes milling or other processes depending on the depth. But what we want to do is catch it when it's shallow. And we want to remove the right amount of metal. What is difficult is measuring the depth of shallow rolling contact fatigue. So knowing, should I grind off a 0.5 millimeter, 1/4 millimeter, what's the right amount to remove, is very hard to measure. And it has economic consequence. So what we're investigating here is the use of surface wave ultrasonics or Rayleigh wave ultrasonics, which we're able to send along the surface of the rail and allow them to interfere with cracks. The principle is shown on the bottom left, and the idea is that waves of different frequencies travel at different depths and will interact differently with different crack types and depths. So what we're doing, this is in collaboration with a peak-to-peak measurement that came out of the University of Sheffield. is looking at measuring simultaneously across multiple frequencies in multiple measurement modes to see if we can characterize these shallow features. And this is what we're starting to see. Each one of these lines is showing a different measurement mode at a different frequency, and we can map that to the depth of what is currently artificial damage, just machine notches, and see that by synthesizing all of these signals, we have a good shot of understanding what the depth of a given feature is. So in this case, we've published based on proof of concept and are now moving on to physical rail testing. Wrapping things up, conclusions are, developments in fundamental understanding of wheel-rail interaction give us, I think, important insights into important phenomena. There are several fundamental research questions that are open, and they give us fertile ground for interesting work. And I'd say we still have much of that work to do. I'll wrap by thanking all of you again, by thanking the team for hosting me for this wonderful visit, thanking everyone online, and of course everyone who's contributed funding to the research. NSERC, the CFI, MyTax, SFU, and Wheel-Rail seminars. Thanks very much, everyone. I'm sorry I'm 5 minutes over. Thank you.
Kevin, that was excellent. Thank you so much. How about some questions from the room, and then we'll weave in some questions from the audience.
Sure. I'll start. Great seminar. As I mentioned earlier, every time you present, I try to pick up and learn something new, and this is a lot. When you're talking about the tread taper of the wheel and the relationship between the difference in radia,
Yeah.
and you're showing that on a graphic that you had a diagonal
Yep.
angle. Is that going to be always directly proportional to the taper angle of the wheel?
Right.
You said
Yeah.
the higher that angle, the more different in radia you have.
Yep.
But I assume that's always going to be proportional to the taper of the wheel design.
Yeah, so great question. In the simplified schematics, I've been drawing these wheels as having like flat taper conical shapes. Our reality is that they tend to be a little more nuanced and sophisticated than that. But you're right to say that the slope of that rolling radius difference plot is directly related to how aggressive that design of the wheel profile is in terms of its taper, whether it's a pure conical taper or how quickly the radius is changing. It's not always linear, so it's not always a straight line, particularly as wheels wear in to their conformal shapes. We tend to see these other shapes emerging.
That was going to be my next question, so
Yeah.
thank you.
One more question in the room, and then I've got several online.
Great presentation. Something I was wondering, you said that it's hard to predict until which depth you should grind it.
Mm-hmm.
How they usually find out that it was not the correct one?
Right. Yeah, it's difficult. So there are measurement methods available to estimate depth. One of the inherent challenges is that the measurement principle typically involves measuring crack length, and then you have to make an assumption about crack angle to convert that into a depth. So that's the inherent difficulty in trying to estimate. And then knowing if you've removed too little or too much can be tricky. Knowing that you've removed too little is easier because there's still RCF present on the surface. There will be post-maintenance roughness, and it takes a bit of time for that roughness to go away. But if you still see RCF present at the surface, it means there was an opportunity to remove more. If you've removed too much, it's almost impossible to know how much too much, because you only know that you've gone deeper than the RCF was. Yeah. Does that answer the question that you're asking?
Sure.
Kevin, I've got several I'll go through here online, and I don't think I'll be able to get to all of them. But are there additional spin creep? Is there additional spin creep that occurs in curves due to the apparent running away of the rail from the wheel?
Yeah. Okay, so it's a great question, and it's a really intuitive way to think about it. When we first think about spin creep, we think, oh, that must be happening as the vehicle is negotiating the curve because it's changing direction as it does that. And there will be some small component of spin creep that comes from that rotational change in direction. but it is a second order effect compared to what's coming from the difference in the rolling radius across the contact patch. The predominant effect that comes from that change in direction as you move through the curve is the lateral creep that's happening at the leading wheel set. Hopefully that answers the question that was intended.
That's great. So another question from the online audience. Wheel flange failures are now the #1 failure mode. According to AAR failure mode, what are your thoughts on the interaction of the flange bearing frogs and crossings with the wheel flange?
Okay. So on the on the one hand, I'm thinking that's an opportunity for me to say something controversial. On the other hand, I think what I'll say is that I think it's clearly an area that is an opportunity for research. I think there's much that we don't understand yet, and it is worth looking more deeply into the fundamentals there.
A couple more questions. Let's go back to top of rail and gauge face lubrication. Is there a way that you could create a model that's based on grade, curvature, tonnage, and speed to know exactly where to place the units in a particular environment?
Yeah, so that is maddeningly complex. I think it's something that we've become better at over the years. For gauge face lubricators, there's been different waves of effort and different threads. Back in the early noughts, late 90s, early noughts, there was some work out of South Africa that was then picked up in North America that used this thing called the de Coker formula to try and take all of these things into account for gauge face lubrication spacing. Some of our railroads have their own methods as well, whether it's total angle of curvature, so the total angle of curvature that has been negotiated between gauge face lubricators, that's often a metric that's used. So in that space, I think there's been a number of different efforts that have resulted in some good practical methodologies. Probably not always spot on because there are so many variables and factors, including the state of the lubricant itself under different conditions. Top of rail, there has also been a number of efforts, and I think there has been progress. I think it's inherently more difficult because it's more difficult to verify presence everywhere all the time.
Yeah.
Active work, though.
You talked some about surface cracks and their length and depth. There's a question from the audience here that asks if you have any kind of update on the effectiveness and the state of eddy current measurements to help with that. Would you care to speak to that?
Yeah, so the use of eddy current to measure RCF depth and shallow RCF depth has been getting better, has been improving. The inherent challenge there, as I understand it, is that eddy current measurements are primarily telling you about the length of a crack, and you need to assume something about the orientation in order to convert that into a depth. So we are getting better at that. There are more and more sophisticated models that map location on the railhead to what sort of angle should be assumed and so on, but there's always that one step of removal from the fundamental measurement principle, which is really what's motivating the bit of work that I talked about in that last part of the presentation.
Understood. One more question here. I know you talked a lot about the conicity of wheels and the taper, but this question relates to the effect of rail cant on wheel-rail interaction. Can you talk a little bit about that? They give examples of our typical 1-in-20 or 1-to-40 cant and other examples of places, presumably internationally, with zero cant over broader distances. Yeah, okay, so, and the question, just to make sure, is about rail cant and not track cant, not super elevation. Yeah, so I think the thing, the nominal rail cant will go hand in hand with the track design and the wheel-rail interface design, and will be intended to direct the load path in the intended way. I think the thing that gets really interesting and sometimes very problematic is looking at the question of dynamic rail cant or loaded rail cant, where what do we see happening as under load, the rail deflects away from that nominal cant. And what does that do both to the contact, but also to the line of L over V versus B over H. It's one of the sources of derailment risk, is that as we load up and see rail cant expand, we can see a higher risk of a rail rollover because we start to see the L over V vector moving beyond the boundary of the B over H. So I know it's a bit of a non-answer, but my answer is that I think dynamic or loaded rail cant is really rich, interesting, and difficult as something to look at. That's great. So, Kevin, thank you again. This was a tremendous opportunity for our team here to learn from you. The seminar was amazing. We have a small gift plus bubble wrap to help you get it back home. So
Perfect.
it's a mug from Realtek. So thank you again.
Thank you.
Maybe one more round of applause.
Thank you so much.
For the folks in the room and the online audience, we'll be back in 2 weeks. We have a great presentation lined up from Metra. So you'll see more about that in an announcement. So have a great weekend.